right. So let's talk about how we can use our root locus techniques to design systems. And I think one of the very first questions, in fact, it was a question that was asked in the previous unit, was can we use this technique to analyze closed loop pole behavior if it's something other than open loop gain that's being varied? And the answer is yes, but we're going to have to kind of manipulate the problem to get it into a form that our tool can solve, okay? So this is generally known as non-gain parameter root locus. And so the question might be, where do the closed loop poles go as z varies? Okay, so let's be accurate here. So the question is, where are closed loop pole locations? That's not legible. Locations as z, the parameter z, goes from 0 to infinity. Well, is this even a root locus problem? Does z affect the closed loop characteristic polynomial at all? Well, I mean, let's work it out. The closed loop transfer function here, y on r, is forward path over 1 plus forward times feedback. And I'm going to do a little trick here. I am going to change this sum into a single fraction. So this looks like s over s plus z over s. So I'm going to treat the feedback path as s plus z over s. And then if I multiply through by s times s plus 1, I get s over s plus 1 plus s plus z. And so here you see that yes, if I vary z, then I will be varying the closed loop characteristic polynomial, which means I'll be varying the closed loop pole locations. So this is, I want you to see this as a root locus type question, even if it's not a carbon copy of our previous root locus examples. And it's going to be my job in the next 6 minutes to teach you how to make this look like our root locus examples. And the key is to start from the closed loop characteristic polynomial. So we just showed that it is s squared plus 2s plus z. And if s is going to be a closed loop pole, that has to be 0. So what I'm going to do is I'm going to massage this. I'm going to manipulate this expression until it looks familiar enough to use our old root locus techniques. So this looks like, I think if I move the z over, s squared plus 2s equals negative c. And then if I reciprocate both sides, I get 1 over s squared plus 2s equals negative 1 over z. And then I can multiply through by z. And this is the key here. Z times 1 over s squared plus 2s equals negative 1. And so this whole procedure was done so that I can get a function of s and set it equal to negative 1, because this negative 1 is the key to all of our former root locus techniques. And so I don't have a good name for this. So I usually, when I do this in face-to-face, I do hand quotations. So this is the quote open loop transfer function. And just to make it clear that it's not the true open loop transfer function, I'm going to call it L prime of S. But in every other way, other than not being the product of the blocks around the loop, this function, L prime, acts like our open loop transfer function from the last unit. What do I mean by that? I mean, our old open loop transfer function, so in the old way, and this in this case old means like 10 minutes ago, we had L of s equals negative 1. That meant that s was a closed loop pole. And our L of S was always written in the form K times G of S times H of S. But what's important is that the thing that was varying was out here. Look at this. The thing that's varying is a multiplying factor out here. So this means that the open loop poles in giant quotation marks here are going to be 0 and -2, because the air quote open loop poles are the poles of the air quote open loop transfer function. This is even more difficult if I can't see that you get that I'm doing air quotes here, because I'm using these terms to mean the function that looks like our old open loop transfer function. So we have something that acts like an open loop pole at the origin, something that acts like an open loop pole at -2, and now we're back into the groove of root locus procedure from last unit. We can say that this is the region of the S of the real axis that is in the root locus, and because it's second order, we're going to have asymptotes at plus or minus 90 that come out from dead center here. Okay, so this is the root locus diagram for this system as z greater than 0 varies. So let's go. When z is close to 0, we get closed loop poles at -2 and 0. When z is in kind of a middle range, we get a critically damped system. And when z is large, we get complex conjugate closed loop poles. The key here was we had to massage a problem that didn't look like it fit our parameters or our mold for root locus into a form that does look like it fits the mold for root locus. And the key was starting with the closed loop characteristic polynomial and making it into a function with the variable in front of a function equal to -1. If you can do that, then you have changed a non-gain parameter root locus problem into a gain-like parameter root locus problem.